Lecture 20. So we'll talk about the second type of inference in Markov logic, and I hope I can show some demo on how to use Alchemy, the system for computing Markov logic, to do some inference. Okay. All right. So let's recall what was the inference problem in Markov logic. So Markov logic combines logic and probability. Now we are exploiting the connection to the probability. So Markov logic, we saw that this can be viewed as a template for specifying Markov networks. So after you construct Markov networks, this is actually a rich, there is a rich literature on computing inference in Markov networks. So you can use the standard method on those things in computing Markov logic inference. Although it actually doesn't work out of the box, so you have to a lot of progress has been made in this area to find a better inference than the typical or standard Markov networks method. Okay, we don't have time to go into all those things, so we'll just give you some talk about some glimpse of this idea. Okay, so last time we talked about two things. One was finding the map state, so most likely state given. Most likely state that is consistent with certain evidence. Now the other one is actually how to compute the probability. Okay. So here is the conditional probability computation in Markov logic. So let's talk about very general things. So first, you're given some formula. You want to find the probability of a formula. Okay. So I give a separate argument here, MLN, just to specify which MLN that we are looking at. But you can forget about that. This is something that we consider under this Markov logic. What is the probability of certain formula to be true? Okay. Now what you know is what is the probability that each interpretation is true. So how do you use this knowledge to find out the formula's probability? So if you go into the very beginning of this introduction to probability that we talked before, that we do, the way that we do is just to sum up all those interpretations that makes the formula to be true. Okay? So it's very straightforward. So probability of the formula is just to sum up all the probability of the interpretation. Okay? That's how we do. The problem with this approach is to store the interpretation, you need an exponentially large size table, which is not feasible. Okay, so in the probability reasoning setting, there has been a lot of work in sampling method because we cannot actually do the most of the time we cannot do the exact inference. So we have to do certain approximate approximate method to compute the probability. So the idea here is instead of computing the exact probability, let's just look at the samples and derive the probability from the samples. Okay, so instead of the general population, you just look at the samples. So S is the set of samples that you generated, and then how many of them satisfies this formula? That is denoted by S subscript F. So S is the whole possible all samples that you generated. And SF is the subset of those samples that satisfy this formula. Okay, so that's the ratio of these two things give the probability of the formula to be true. Of course, it actually depends on the quality of the samples if we want to make this idea to be true. Okay, all right. So let's talk about very beginning of the sampling idea. So you want to use sampling to do a lot of prediction. Okay. Now the basic idea is you draw some samples from some sampling distribution and compute some approximate posterior probability, meaning that you know certain thing is observed. Okay, among all the samples, you know that this evidence is true. Then you only look at those samples, and from that you compute what is the conditional probability. Okay, we'll talk about the examples soon. But basically, this number should converge to the true probability. Okay. So why do we do samples? So sample can be used in two ways. One is to do the inference as we speak today, and next week we'll talk about the learning. We use samples to do the learning. Now for the inference, as I just said, it's infeasible to compute exact answer for the most of reasonable size domain, so we are going to use samples to do. Now learning can also use sampling when you don't actually know the underlying distribution, so you know this, you derive this probability through probability from these samples. Okay. All right. So how do we do the sampling? So the first step is just to find any sample, some random sampling. So let's say we have 0 to 1. Okay. Just pick any number from 0 to 1. You can implement this with any Python code, like Python function like random. Okay. Now this number u between 0 and 1 is an arbitrary random number. Okay. First of all, finding true random number is really difficult problem in theory and as well as in practice. But let's assume that this can be done for now. But then after you do this, you have to map into the sampling distribution. Okay. So here's an example to illustrate this. So we know that when you draw some maybe balls, there's a 0.6 chance that you get the red ball, or 0.1 chance with green ball, and 0.3 with blue ball. So suppose this is the underlying probability distribution that you know. Okay. So how do we generate samples from this distribution? The idea is we are going to map the u that you extracted in the first step into this mapping. So if u that you got in the first step is between 0 to 0.6, we'll draw the red as the sample. Okay? And for the other two cases, it's similar. Okay? For instance, you've flipped the random generator and it gives 0.83, then you will draw the sample which is blue. Okay? So if you do sampling, the idea is if when you do this, first you got 0.83 as the random number, so you got this one. The next time you got maybe 0.1, okay, as a random generator, you got the first red, and maybe also 0.2 next time, so you got the second red, and so on and so forth. So if you do this in 8 times, let's suppose that we got these samples. And from this, we can forget about the probability distribution table. We only look at the samples and do the posterior probability. So what is the probability that something is true, given something is true? What is probability that something is true? So for instance, if I know that the probability of the ball is either blue or green, what is the probability that ball is blue? Okay, so what is the probability? So you can, if you look at the samples, there are 3 balls that is either blue or green, right? So that is 3, and how many are blue? 2. So there's a 2/3. What about this in terms of the actual probability distribution? This is actually not the same, right? Because you have the these two, right? So it's actually 0.1 plus 0.3 over 0.3. So this is actually 75% rather than 66%. So it's actually slightly different. Okay. But the point is, when you have more and more samples, these sampling probability, the probability that you obtain from the sample, should approximate the actual probability. Okay? Are we together? All right. Okay, good. So there is a lot of sampling method, and I don't want to go over all these things. We don't have time to do that, and that's actually not relevant for this class. So we will look at only one sampling method and one category first. So what is called MCMC method, Markov chain Monte Carlo method. Okay, and among these, and there are actually several algorithms inside this family, and we'll only look at one of them. Okay, but what is actually the general idea of Markov chain Monte Carlo method? You probably have heard this name a lot. Maybe if you took Intro to AI, you have seen those kind of sampling methods. I'm sure there are a lot of sampling that you studied in Intro to AI, like rejection sampling or force sampling, or there are a lot of sampling methods. Now this sampling method works well for Markov logic, and as well as also many other domains. Now the strange thing about this sampling is you're not really generating the random samples every time, okay? you start with some random samples initially, okay? That reflects the true probability. But after then, you select the next sample based on the previous sample. So when you do this sampling, the second sample versus first sample are not very much different from each other. In fact, actually they are dependent. Okay? So when you draw this thing, what happens is you draw the first sample and then you generate another sample based on the first sample. You actually slightly change the first sample and do this thing repeatedly. And this chain is called Markov chain because as the name Markov implies, the sampling here depends only in the previous state. Okay? And they're actually very much alike to each other. Now, this seems to be not in the spirit of random sampling, but it turns out under certain assumptions about the MCMC, you can say that the sampling, the samples that are generated from this method converges to the probability, true probability. If the sample size is, of course, large enough. Okay? So, let's see actually how this works. We are going to see the algorithm statement later, but let's start with a simple example. Okay? So, this is the Gibbs sampling. Okay? And we have only 3 nodes, B, A, C. Okay? So, as I said, the idea is the sampling is not independent from each other. Each sample is not just from scratch, okay? You are actually making the next sample based on the previous sample. And what you do is only change one variable in the sample, okay? So between the two samples, the difference is only in one variable. Could be one variable, it could be actually the same, okay? All right, so let's look at this. So first, we have these 3 variable B, A, C. Let's imagine that we start with this initial sample. So B is positive. I denoted by this plus B, plus A, plus C. So every variable, all the variables are Boolean, and they are all positive. Okay, so they are 1. Now we want to compute the probability, which is this conditional probability, where C is already observed to be true. Okay. Now we want to prove this one. So instead of the previous sampling that I said, just generate all the samples and then look at only those samples that satisfies the condition, this is actually different. We only generate samples that makes the condition to be true. Okay, that's actually one advantage. You don't have to necessarily generate unreasonable samples. Okay. All right. So let's start the procedure. Okay. For now, for simplicity, let's assume that each variable can be sampled in uniform way, so half and half. Okay. If everything is there is a choice, then let's say half and half choice. Okay. All right. So initially, we are given this sample. So B is positive, A is positive, and C is positive. Okay. The procedure actually alternates between the non-evidence variable. Here, evidence variable is C. C is observed, so this is called evidence or condition. And there are 2 non-evidence variables, which is B and A. So the procedure will alternate between B and A. So B select the variable, select the value for B, and then select value for A, select value for B, select value for A, and so on and so forth. Okay, and in all those samples, C will be fixed to be positive. Okay, so this is the first one. You don't touch on the C part, but let's actually start with B. Let's do the sample B. Okay, as I said, it's a 50-50%. So given this thing, A and C is to be fixed. They are fixed to be positive. But for B, we can select either positive or negative, or 1 or 0. Okay, are we together? Okay, so here it turns out that, so here the A and C are observed, so they don't change. When you do the sample, we are only sampling one variable. Okay, and sampling one variable is actually pretty straightforward to do. And it turns out that it is, maybe the coin was flipped to tail, so it is negative. So we got the next sample. Now, as I said, the first sample and the second samples are almost similar except for the part B, right? Okay, good. Now this time, next time, we are going to sample A. Okay, so so now the second sample is minus negative B, positive A, positive C. So we are going to sample A now. Okay, and A has half and half chance to be true. Turns out that was negative, so the coin was again tail. So now we select another sample which has B to be false and A is to false and C is to be true. So this is the next sample. Okay, so we got 3 samples, and then we repeat these things over and over. So we do the sample B. Okay, again you have to fix A to be negative and C is positive because that's the current sample, and now we have to select B. Okay, turns out that B is again negative, so it is not really a 50-50 chance, but somehow, even though it is 50-50, it is possible to generate this. Okay, now you do the sample A, then you have to fix B to be false and C to be true, and you have to sample A, or this time again false. Okay, sample B, or this time is true, and so on. Okay, so we got 1, 2, 3, 4, 5, 6 samples. So what is the probability of okay, let's say what is probability that B is true given C is true? Okay, what is the probability?
6.
So yeah, we have 6 samples, so that's actually the whole sample. How many of them has B to be true? 2. I think it's 2, right? The first and the last one has B to be true. So there's a 1/3 chance. Okay? Now, as I said, I meant this to be half and half chance. So that means P of B given C is actually the same as B because it's actually independent. Okay? So I was expecting 1/2, but from the sample I get 1/3, which is not very wrong. Okay? But this is anyhow very small samples. Okay? We together? Good. So you mastered one technique already. Okay? All right. So here's an algorithm for Gibbs sampling. Okay. So just to recap what we have done in the example. So first, we call it state. Okay. Each sample can be called as a state. So first, we actually do random assignment. Okay, and then we are going to generate a number of samples. Samples is the whole number of samples that we want to generate. And what we do is for each random variable x, sample x according to x probability of x given its neighbors. Okay, and this x will update the current sample, so that will be the new sample, and we iterate this over. Now the algorithm actually doesn't say about the condition part, but you can actually easily add that. Okay, and when you say for each random variable x, we only talk about the random variables that doesn't involve evidence variable. Okay, all right. Are we together? Okay, good. All right, so let's look at another example for this. And actually, before we do that, I told you that sampling one variable given the current sample is actually easy to do. But let's see how easy that is. Okay, so here the idea actually works well if we can compute the next sample easily. Okay, there are some cases that MCMC method does not work. When finding the next sample, it's not that easy. Okay, and also it doesn't reflect the assumption about MCMC, but we are not going to talk about that here today. General idea, again repeating this, for given the number 1 to n, we are going to sample the value of xi given the rest of variables while fixing the evidence. Okay, so let's actually look at how we find the probability of A given B, C, D. So this is actually, let's say, the first step. Suppose you are going to sample A based on the current assignment to BCD. Okay? Are we together? Okay, so here small letter A, B, C, D represent particular values assigned to the random variables, capital A, B, C, D. Okay? So what is this probability? Now we are talking about this. Okay? We are giving an example of this probability. So here, this is conditional probability. We know the probability of A, B, C, D, okay, divided by the case when A is either true or A is false. Are we together? Okay. So here, I'm going to write this as A, where this A can get the value either 1 or 0. And we have to add up those two probabilities. Okay? So in the denominator, you have P, A, B, C, D when A is true, while B, C, D has a fixed value, plus A is false, and B, C, D again have the same fixed value. Okay. Are we together? Okay. All right. So, in fact, it turns out that we don't actually have to look at the probability. We can actually look at the unnormalized probability because the denominator for each probability is the same. Okay? So let's actually just look at this unnormalized probability. Do you remember how do we compute the numerator? How do we find the probability of A, B, C, D in the Gibbs distribution like here? Multiply. Good. So this gives me phi 1 AB times phi 2 BC times phi 3 CD times phi 4 DA. And let's actually write AD. Okay, so this is the numerator. The denominator is also the same, where it actually has two terms. Okay, so here A, phi 1 AB, phi 2 BC, phi 3 CD, phi 4 AD. Okay, are we together here? Okay. Now, surprising thing. What is surprise here? What is a surprise in this equation? Okay, let me show you what is that. They have the same factor. There are actually two common factors. This can be cancelled out, right? Let's look at what remains. Okay, so if we do that, you will get phi 1 AB, phi 4 AD. And the numerator here is just, okay, let me just write the numerator here because it's now small. So phi 1 positive A, B, phi 4 positive A, D, plus phi 1 negative A, B. Okay, whatever the value of B and D is. Okay? Okay? So if you want to compute the probability that A being true, then one of them is already in the denominator. Right? So what you have to figure it out is actually only these two guys. You have to know what is this value and what is this value. Then you can compute the probability of A being true given BCD. Okay? So in other words, what happens here is all these things right here, okay, is actually proportional to this. Okay, so the last equation, okay, you can say that the probability of A being true given BCD is proportional to the these two factors. Okay, multiplication of these two factors. Okay, which means when you look at A, you don't have to look at D. I'm sorry, you C. Sorry, because B and D are the Markov blanket, and that gives enough information about A. You don't have to know C. Now let's think about this in a bigger picture. So suppose A is related to A is connected to B and D, and C is connected to maybe 100 other nodes that are here. So what this sampling means is you don't have to look at all these 100 plus C node when you do the sampling. You only need to look at the neighbors of A to find the next sample, which is typically small. In the worst case, of course, it could be the whole. Okay, because if it is fully connected graph, then the Markov blanket is actually the whole, the rest of the network. But in many cases, it can be localized. And we actually talked about this before when we talk about the theorem that guarantees between the independence assumptions and the Gibbs distribution. Okay, so this is actually the same idea. Perhaps it's easier to look at the examples, so let's do that. But I want you to remember this fact. Okay, so given the whole derivation, what comes after the last step is to find this next sample, you only need to know the relationship. We only need to know the anomalized probability related to the Markov blanket.
So can you explain this last step again?
Last step? Which? Okay. So from here to here?
Yes.
Okay. So if you want to know that P is, what is the sampling to be positive given BCD? Okay, so B and C and D have certain particular values, 1 or 0. Okay, in order to do that, what the last thing is saying is you have to know phi 1 positive A B, phi 4 positive A D. Divide by phi 1 positive A B, which is the same thing as the numerator. Okay, when this is the probability that you're going to get the positive A. There's also the negative A part, which is this. So to find this value, what you need to know is this number and this number. Then you can find this number. Okay? You actually asked this before when we have independence assumption. How does it change the normalization factor? Right? This is actually this instance. When you can isolate the graph, the normalization factor also changes, but it cancels out in both numerator and denominator. Okay, so the probability remains the same. Okay, so maybe that was a bit unclear if you have two complex equations. So let's actually look at the particular example. So let's imagine that we want to compute the probability of A being true or false given C is false. Okay? Actually, you know what? Let's actually forget about this. Okay, let's forget about the evidence. Let's just generate the samples. Okay? Let's imagine that we are given this sample. Okay, so first random initial assignment. Okay, so A is false, B is false, and C is true, and D is true. Okay, we are going to do the Gibbs sampling on A, okay, which means that the next sample will have fixed value for B, C, D, which is the current one, but we have to find the other one. According to the equation that you just saw, okay, the probability for finding the next sample is this one, B, P of A given what?
B and B.
So I have to find, and this only depends on B and D, and B is currently false, and D is currently true. So I have to compute this probability, right? Probability of A being true or false, given B is false and D is false. And as I said before, we have to know only two values, okay? So one value is, let's say, a normalized probability measure for A being false, given B0, D1. Okay, actually, I don't have to even do this. Let's say some factor. Okay, because probability is just a multiplication of this with respect to whole distribution. Okay. Another thing is, of course, I have to do something about it. I'm going to use just the same name for here. Actually, let's say pi 0, pi 1 to denote false and true. So this will be 1, B0, D1. I have to compute these two numbers and then normalize it. Okay. All right. So what is the this one? I can only look at the factors or potential functions related to these random variables. So that gives me phi 1, I believe, A0, B0 times, and this is D, right? So pi 4, D1, A0, right? What is this number?
30 times 1.
30 times 1, so that's actually 30. Good. Okay. The next one is phi 1. Okay. So what is the phi 1 A1 B0?
1.
Okay, so let me just copy this. T1 A1. Okay, say it again. 1. Okay, and phi 4? 100. So that's this. So then, what is the probability of A being true, given B is false and D is 1?
100 based on 30.
30 divided by 130, 3 out of 13. Right?
Yeah.
So that's the probability distribution. That's the probability that you have to sample the next one. So it is very likely that a sample will generate A to be true, right? However, that doesn't necessarily mean that it's always the case. Are we together? Okay. So let's see, because here it seems more probable. Let's say we chose A to be true. Then what is the next sample? The sample is, of course, A1, B0, C1, D1. Now, when we look at this sample, we didn't. So when you find from the first sample, point from the first to second sample, we didn't bother to look at C, right? Okay. Now, after this step, we have to iterate this. So let's say we are now going to sample B. Okay, which means we are going to compute the probability of B given the rest of the variable to be fixed, but we don't have to look at all the rest of the variables. We only need to look at A, C. And currently they have A1, A to be true and C to be true. Again, we have to look at the two numbers. Okay, so the first one, given B is true, given A1 and C1 is true, and the second one, B is false. I'm sorry, let's start with false. False, A1 is true, C1 is true, B is true, A1 is true, C is true. Okay? And I believe that you can compute this number in the same way. Are we together? Do we want to do this exercise? Okay, let me open the Socrates and find this probability of B to be true given A is true and C is true. Okay? But before we do that, any questions? No? Yes?
If you
Yes.
We do the sampling at all. We just use these possibilities to compute the factor of the possibility.
Each sample is not really true sample, right? So when you select enough samples, that it goes to probability, right?
Yes, but we are computing the possibilities to generate the sample, right?
Oh, good question. What is the size of the probability table that you have to store here?
Explanation.
It is not. Here, I'm not talking about the general one. So that's actually a very good question. Why do we bother with computing this probability? Each of the time, of course, we have to compute this number, but this is actually very quick to compute.
Yeah.
You understand? Because we have fixed all the other values. You only need to multiply two factors. In comparison, if you have to know the probability table for the whole variables, then you need the exponential number of this, the exponential size of the table.
Yeah, but eventually we are going to sample all these variables, right? So that means
Yes.
eventually we have correlated all these possibilities, fixing the automatic this and iterating each one.
So are you talking about why do we bother to compute the probability each time?
Yeah, I think it's the same if we compute all these possibilities beforehand. And then
But note here that, maybe I'm not getting the correct question here, but let me say for the sake of the time. For here, each probability computation is actually simple to do. Okay? Now, in fact, sampling only one variable out of the rest is actually very quick to do. And you don't have to store, you don't have to compute this every time, because once you know this, you can actually pre-compute this table and you can just look up the table. Okay. On the other hand, if you want to compute the arbitrary probability in the sampling, then I don't know for sure what variable to be conditioned on and how many values that have to be. Okay, so we can talk offline, but I guess there's something. Yeah, that's a good question. Just the thing is, if you want to do in the general setting, then the probability table is too large to store. This is actually simple. Okay? But the detailed thing we can talk offline. All right. Okay, so then let me open the Socrative. Okay. So this should be one number, so let me just say this one. Okay, let's start. Let me show you this again. So so the question is, what is this probability? Let's say what is the probability actually B is true. Okay. So what is probability of B being true given A is true and C is true? You can talk with your peers if you want to.
If I had submitted my answer and it still gave me this.
And not able to submit.
Okay, let me check on that.
I did it twice and it looks like it.
How many of you could submit? Yeah, you did, right? So, any problem?
Keep popping up.
Oh, okay. Maybe I just set up to be unlimited response. So you can update if you want, but if you have submitted, don't worry. Okay, so I got 26 answers or 27 answers, that should be enough. Or 28 answers now, so everybody actually voted. What? We're talking about, okay. So what is the answer?
1,000 by 1,000.
1000 by 1001. Okay, so let's see. Yeah, looks like most of you did good. There were 2/3. Okay, so there's a minor mistake. Okay, I don't know why 2/3 is there, but basically that's the answer. So just follow these computations, you will probably get easy. So I'm happy with that. So let's move on to the next. Okay. All right. So then the next thing. Okay. So then the next thing is. So previously this was actually a simple graph and we iterate over. Now sometimes you don't actually have to worry about the whole graph. Okay. So let's imagine this. We want to compute. Okay. First. The general case is we are going to compute the probability of something to be, some formula to be true based on some other formulas to be true. But most of the time what happens in the probability query is you're given the evidence as a conjunction of ground atoms or ground literals, and you want to know the probability of a single variable, single literal. Okay, so for instance, if you know that A is a smoker and B and A are friends to each other, then what is the probability that B has a cancer? So this is a very typical way to do. So usually this part is a single atom instead of general formula. And again, the condition is also just a conjunction of these literals. Now if you know this one, the nice thing about this simple form is we know exactly what is the value of Markov blanket. Okay, so we can actually construct the graph network that is only relevant to the query. Okay, you don't have to look at the whole graph. Okay, so I mean, to answer this query, do we have to look at the whole ground network? And I just said it's not. Okay, no, you don't have to look at it. For this particular query, you can only look at this part, and I'm going to explain a bit more about how to find this ground network that is relevant to the query. But as you can imagine, these are the observed variables, right? So they actually cut the information flow. So knowing these values does not affect the probability of cancer of B. Okay? Now the other values that is not cut, like smokes B and friends BB, you still have to consider in your network. Okay? But the nice thing about this is this part has fixed value. Okay? And this part is to be sampled on, but there are actually a small number of samples to do. And when you do the Gibbs sampling, you just iterate over these 3 nodes. Okay, that's enough. Imagine that if you have thousands of nodes, you don't have to look at all the Gibbs sampling going over all the 1,000 variables. Okay, you only look at, even then, you only look at these 3 variables. Okay? So this is actually the algorithm, and I'm going to talk briefly about it, and we are going to look at the example again. So initially, the network to consider is empty, and there's a queue that we have to consider. And the algorithm is actually very simple. It's basically just going to the front, just adding more nodes that are connected to the current node, except that the node is actually observed variables or evidence, then you don't have to go beyond that. Okay. So first, what do you do? Repeat is take the node from the queue. Okay, and this queue is now remove this node from the queue, and each time you add the node to the network, if node is evidence, then you skip this part, adding part. But if it is not an evidence, you add the neighbors of the current node. So you expand this node on and on. But if it is evidence, you just stop there. And you do this until every queue, until every node in the queue was emptied out. Okay. So maybe that's actually too much. So let's actually look at the examples. Okay. So here we are given this brown node to be the evidence node. Okay, so we know the values of these because that's actually what we have, and we want to know the cancer of B given this, right? So according to the algorithm, let's actually imagine network and queue here. Okay, so first, what is the current queue? So Q will be initialized with the query node. So that's a cancer. Okay, let me write COB. Okay, so this line put the COB to the Q. Now we are going to do the repeat. Okay, so first node will be now selected the front of the Q. So the front of Q is actually COB. There's only one. So the node here will be COB. Okay, so we are done with the first line of the repeat. And we have to remove node from the queue, so now the queue is empty. Okay, now add node to the network. So the network will have COB, and we have to check whether this node COB is evidence or not. It is not. So what we have to do is add neighbors of node to queue. So what are the neighbors of the cancer B? There's only one neighbor, which is smokes B. So we add smokes of B to the queue. So we're done with the first iteration. Are we together? Okay, so next repeat this. Now node will be initialized with, node will be the front of queue, which is now SOB. And we remove node from the queue, so queue is now empty. And add node to the network, so SOB will be in the node. So node is not in evidence, then we have to add the queue. So what are the neighbors of SOB? There are actually 4, right? Except for the cancel that we did. Okay. So friends AB, friends BA, smokes A, and friends BB. So now the network contains these things. Okay, and we have to. I'm sorry. These. Oh, I screwed up. These were all should have been going to the queue, right? Yeah. Okay. Let me. So let's go back. So this is fine, right? We have to add the friends AB, smoke A, friends BA, friends BB to the queue. Okay? Are we together? Okay. All right, so that's the queue. And we are done with the current iteration. And then we go to the next. So node is now front of queue. Okay, so now node is front of queue, which friends of AB. Okay, and we remove node from the queue, so we removed it, and add node to the network. So that's the friends of AB. Okay, and if the node is not evidence, that we add, but friends of AB is actually the evidence, so we don't do. Okay, good. So we stop there. Okay. Now we go to the next one in the queue, which is smokes of A. In the same way, this one doesn't increase the queue, but it only consumes the queue, so this will be smokes of A. Same way, friends of BA is also the evidence, so friends of BA will be there. Okay? And in the last step, I'm not going to actually bore you here, but the last step, this one will be added to the network. Okay? But there is no further neighbor to add, so we are done. So these are the whole network, which will be the network shown here. Okay? And when you do the Gibbs sampling now, these have the fixed value, so we don't need to iterate over these random variables. You only iterate over these variables. Okay? Are we together? Good. All right. So, unfortunately, this Gibbs sampling is not actually the main approach to compute Markov logic. There are some problems that I will probably not go into the details, but in Markov logic, some rules are definite rules. So some formulas has to be always true. And Markov logic, Markov chain Monte Carlo method does not actually work well if the probability distribution is not smooth. Okay, so there's actually some slice sampling that we have to use here. So in the end, you don't have to worry about a particular method, but there is actually a way to solve this problem using the idea of logic plus the probability. So we have seen the walk set algorithm. So there is a algorithm called MC set that combines the idea of MCMC with work set algorithm. And I do have slides, so if you want to take a look at it, you can do. But let me actually skip this now. Okay. The reason that I'm bringing up this algorithm is because the Alchemy uses this as a default inference. Okay, it's not the Gibbs sampling that it used. All right. So remaining time, I'd like to talk about the Alchemy system. Okay. So this is an open source software managed in the University of Washington. Actually, the group which invented Markov logic. Okay. So we are going to use this for inference and the weight learning. So these are the programs. We are going to use these two programs, infer and learned weights. Okay, and there are certain options that is good to know, and there are some options that we have to know versus some other options that is good to know. Okay, you have to supply two files. One is the Markov logic network file, and I'm going to show some example. And there's also the database file. Okay. Here's a very simple example. So there are three atoms: P1, P2, P3. And P1 gets the value, P1 gets the weight 3, P2 gets the weight 1, P3 gets the value -1. Okay? So if you look at these things, so P1, P2, P3, that each of them can be either true or false. So how many interpretations are possible? There are 8 interpretations. But now we can actually say which interpretation is more likely than the other. Okay, so among these, which one is the most likely? Which interpretation is most likely? Obviously, the one that contains P1 and P2, right? Because if you start to include P3, then you get the penalty, -1. So the most probable model is P1 and P2. Okay, so this gets the highest one. What is least likely? P3, because it's actually the negative. Okay? If you don't select any of them to be true, you still get the 0 as a weight, or e to the power of 0, but this one is actually smaller. Okay, so how do we encode this into the input language of Alchemy? So the syntax is slightly different from ASP. It is in some sense similar, but it's also different in the sense that most confusing part could be the constants is now capitalized and the variables is in lowercase. That's opposite to ASP. Okay? So first, what we do is we declare the objects. So the number is from 1 to 3. Okay, so we write this set notation to say number goes to 1, 2, 3. And the predicate declaration, here we use, we can just write a predicate name followed by the some placeholder. Okay? Now this thing is actually this number here. Okay? So this declares that there are predicates to consider P1, P2, P3. And then you give the weighted formula, which is written as is. Okay? Now you can actually give, yeah, let's stop here. Yes, question?
So the delimiter is just a new line?
Yes,
okay.
yes. There is no period at the end except for the last one that I want to tell. Okay, yes?
Did you mention those two numbers same or they are different?
Those two?
The number on the top two lines, first two lines. So first you declare a variable number.
Right.
And then when you write P num, what does that mean? So that num.
That's just a predicate declaration. Yeah.
So it says that it can take only those values.
Yeah. Yes, I believe so. Yeah. Although I'm not sure. Actually, that's we'll see the. Yeah, I think that's the case. Yeah. Okay. So that's actually the types. So when the P populates the argument, what are the possible values there? Okay. All right. So unlike ASP, we don't have to. We shouldn't actually end with period. Period has some special meaning. There is something called hard constraint, which basically means the weight is infinite. So infinitely positive. So this one must be true. Okay. if you don't satisfy the hard constraint in theory, what that means is the interpretation gets the weight 0. Okay? Are we together? So now let's think about it. If I give this one, in addition to the previous weighted formula, what is now the most likely most likely model? Hmm? P1 and P2 is no longer.
That not say.
Okay, so I said this one, this exclamation is actually negation. Okay, and the Carlo symbol is actually the comma is in ASP. So what it means is P1 and P2 cannot be true at the same time. Okay, so then the most probable model becomes P1 only. Okay, if you include P2, this interpretation will get the weight to be 0. Okay, or you can say it gets infinitely negative penalty. All right. Good. So then I think you are ready to look at. So here is the command line. So infer is the program name to use, and -i is to specify what is the input file. So I called the previous file to be example.mln, and you have to specify the output file. So -r, and then give any output file name. I just happen to give out. And -e is a database file specification. Here we are not using the database yet, so you have to give some file, which is actually a blank file, and I called it empty.db. So this file is just a blank file. And then I have to give a query predicate. I want to know the query for the, I want to know the probability of the P. So if I execute, I think this was the second program. Okay, if you do that, it will show the marginal probability of each of the ground atoms. So P1 to be true is most likely, P2 is true is 0.73, P3, okay, right? Are we together? Yes?
So those numbers right there, is it basically saying, so you have a set of possible stable models, and that number there is the probability that that predicate is, yes.
The probability of P1 to be true. So you have to aggregate all the interpretations that make P1 to be true. Okay, so probability of all these interpretations. The marginal probability of P1. Okay. All right. So next one. So I want to flip the coin. So there are actually 20 coins, and I want to express the thing that it flips head. Now, this is actually a very simple program where you specify these two lines. Okay, first, this sign is actually for the comment. Okay, now we declare the flip has the 1 to 20. And we have ground atoms of heads or flip, but we don't specify any rules. Okay, so what happens? So if we want to do this, then we are not giving any information about whether the, each of the coin is head or tail. So we expect that this is actually uniform distribution. So head of 1 and head up to head of 20 should be 0.5. And in fact, actually, that's not the case. By the way, these examples are coming from the Alchemy tutorial. Okay, so you can look it up there. What I want to tell you is actually the, contrary to what they say in the tutorial, this example actually didn't work. Oopsie. And why is it not typing? Okay, so Okay, so so that's actually the uniform.mln file that you just saw. Okay, it has segment fault. Okay, so it does not work. So instead of that, what you can do, it turns out that different from what they say in the tutorial, you have to give certain formulas. So I give here head of f gets the weight 1, and not head of f gets also weight 1. So that's actually equally likely, right? So actually, let's use this file. So this is the whole program that I give. Okay, so let me put output. So until here is actually the console output, and the output file will contain this. I just appended to show the output directly. And as you see there, actually I put only the 5 Yeah, so I only gave 5 coins, so that's why it shows only 5 head. So each of the probability is actually 0.5, about 0.5. As you see, this is using MC set sampling that we briefly mentioned. So it's not actually exact computation. So that's why you see sometimes 0.51, sometimes 0.49. Okay? Okay, good. Then let's talk about binomial distribution. So here we are not necessarily saying that the probability of coin is, the coin is actually fair. So it could be biased coin. So how do we model the biased coin? It's in fact interesting to see that how are you going to say the formula. So the formula is now heads of f only. But what weight had we have to assign so that the head being a head of coin being true is 0.7, 70% chance. How do you specify the weight? You cannot actually give 0.7 heads f. This does not work. Why? Because the way that Alchemy or MLN computes the weight is exponentiated sum. 0.7 as a weight is not the probability. Okay? So if you call 0.7 there, okay, what will happen to this probability is e to the power of 0.7 plus, when this is false, e to the power of 0 over e to the power of 0.7. This is the actual probability that head will be true. Okay, go back to the definition of the probability. Okay. Now, instead of this, what can you do is you can give, if I want to say head is 0.7 chance, what you can do is give log of 0.7 over 0.3. Okay, so this is heads of f. So, which means that each head will get 70% chance to be true. Why this works? Well, let's look at the probability. The probability now will be e to the power of log of 0.7 over 0.3 when the head is true. That's actually here, right? Over when this is false. What is the weight that it gets when it is false? 0. So you get this one. Okay, I think I probably need more space, but let's say this way. So what is this probability? Or what is this number? Simplifying this number. That's 0.07 over 0.3 and 0.7 over 0.3 plus 1. Now if you multiply everything by 0.3 in both numerator and denominator, then you get 0.7 over 0.7 plus 0.3, which is 0.7. Okay? So assigning the weight is a bit complex because it's not the probability that you record in the weight. Okay? But you can actually model the probability using this equation. Okay, are we together? All right, so then using this, how can we do this? Actually, let's skip this part. Okay. You can actually compute log of 0.7 over 0.3, and you can do, I don't know what is that number, so I didn't actually put it here. So let's actually skip that, okay? But here is another example. Suppose you give 0 as the weight. What will happen? What will happen to the probability of head being true or false?
Not exactly what this was very small number.
When you give 0, when the formula is true, what weight do you get?
0.
E to the power 0, yes. Okay. What is the weight that you get when head is false?
50 by 0.
So that's 1/2. So you can actually get the fair coin if you put 0 as the weight. Okay. Okay, let me get that one. How much time do I have? Okay, good. Because, yeah, okay. Multinomial distribution. Now, not only we have only 2 values, but let's suppose the dice, we throw the 20 dice, and each of dice has 6 faces. How do we do that? We can't say the types is throw. Throw is 1 to 20 runs, or 20 throws, and face is 1 to 6. And the predicate is outcome, which means that in the first throw we have maybe 1 as a face, or second throw we have 2 as a face, things like that. So these are the predicate that we throw. Something that we have to say more is each of the throws should have exactly 1 number associated with it. It's a function, right? When you throw it, it only returns only 1 face. And that's a kind of uniqueness and existence assumption that we did in the ASP. Okay? For each of the throw, there should be a unique outcome. So if you throw it and there are 2, if you throw, okay, and it returns face, or some face, and there's another face f1 that is different, f prime that is different from f, then that outcome should be false. So we don't want to have outcome of 1,1 and outcome of 1,2 to be true at the same time. That's not possible. So we have to say this. And also each of the face, each of the throws should have a face, at least 1 face. This is the existence constraint. Now in ASP we did this kind of thing, use the cardinality constraint. There's no cardinality constraint in the Markov logic, so you have to write the full formulas. Okay? So this is the file that you can write. Okay? In fact, there's some technical reason that this solution is actually not ideal, although it actually works. So what they introduce is instead of writing those existence constraints, you can write predicate, you can declare the predicate this way. So that then this is same as writing these 2 lines. Okay? So theoretically they are equivalent. Okay? But if you do this way, then Alchemy knows more about the distribution, so it can compute the sampling data. Okay, are we together? Okay, so let's look at the example. So for technical reason, again, if you look at the tutorial example there, it doesn't work. This is actually from the tutorial, but you can actually easily introduce some bogus atom I and just give 0 as the weight of that. So just give any simple formula there, and then it should work. Let's actually look at that thing. Okay. So So this is doing the sampling, and then you see at the end, you see the outcome of this. Okay, so each of the run, okay, you see that the chance is 1/6, which makes sense. Okay, All right, so let's actually go a bit more than this. Smoking example that you saw before. Okay. Okay. So this is how you encode the smoking example. So there's a cancer person and friends person, smoke person. And actually, to answer Arindam's question more correctly, Alchemy actually can find out what this person range is over when you look at the database file. Okay, so you don't always have to pre-specify the range. Okay, so let me actually show you that example. So this is smoking.mln, which contains the rules that you saw before. Okay, now this time we are going to use the database. And here database is written in this form, which is very simple one. We know that I didn't pre-declare, but there are A, B, C, D, E, F, G that is mentioned in the database file. So Alchemy knows how to populate these variables. And we say that A is a smoker, B is not a smoker, and C is a smoker. And we give the bunch of friends relations. Okay? Okay, so how do we compute this thing? Again, you give input file, and output you can name anything. Now, evidence I have to give the smoking.db as the input. Okay, and query is maybe smokes, and maybe I can also say cancer. Okay, and out. So this is the probability distribution. So as you see, not all of the people are here because those people are observed. So we know for sure that somebody smokes or not. So that's either 1 or 0. So Alchemy does not show. For other people, there's a chance that they are smokers, depending on their friends to the smokers. And these are the cancer rate. Okay? All right, so that's how you do. Next time, we are going to learn how to learn this weight, because I give just weight to be negative 2.9 for 4. I believe this is actually 0.05 chance. If you have log of, this one is actually log of 0.05, 0.95, which means that 5% chance this rule can be true. Okay. And the next one is actually 30% chance. But this is actually what you pre-specify. I know some of you want to learn the weight. Okay, for that you are going to use the learn WTS file. And if you do that, this weight is actually learned from the data. Okay, so that's what we are going to study in the next class. Any question? Okay, so then let's stop here and let's